Okay, good morning, class. I'm Warren Heffler, and this is Section 5. So all of you guys are signed up for Section 5 of this lab? Okay. So this is a lab course, not a lecture course. Yet, here we are in a lecture room. You know, the thing is, it's very difficult to go into a lab without having any information about what you're doing. It can be pretty confusing. So I think it's worthwhile having a little bit of a discussion. Yet, I'm not really going to go into detail in any particular topic because this is not a lecture. So I'm going to try to give you background information that you need to do the lab. Pay attention in your other classes. And try to apply what you know to what we're doing, right? Try to find the connections. I think one of the rationales for a course like this is to have you discover things in a lab environment, hands-on, and then with that knowledge, with that personal experience, you can perhaps learn some of the concepts more easily that you get in some of your classes. So it doesn't only go one way where you learn in the book and then you have the experience doing something hands-on. It can go the other way. You're doing something hands-on and then it helps you understand what's going on in the book. So that's part of what we're doing. Okay, so especially this semester, I think it might make sense for us to have a lecture time first thing in the morning for every class. And we're not going to vary from the Friday morning thing either yet for this semester. This is a 3-semester class. Keep that in mind. Right? You know, so we're really going to hang out together for a long time. We're going to get really comfortable with each other. We're going to know all of your names. You guys are going to feel relaxed. You know, this is a long time. I mean, look at it. It's 8 o'clock in the morning, and you know we potentially can keep going until 1 o'clock. So that's a long time. So obviously, you know, I don't want to grill you for the whole time, that kind of thing. We want it to be a learning experience. You need to be relaxed. You need to be natural about what you're doing, and as long as you're there and you're trying and you ask some questions when you don't understand, we should be good. Okay, so I'm Dr. Heffler, and this is my assistant in the back. This is Thanda.
Hi.
And Thanda has been working with me this summer, along with Brandy. You guys know Brandy? Brandy worked in the SHORE program. You guys heard about that opportunity? Not so much? I was trying to encourage some people to apply for that. I think it was a really good opportunity. What do you think, Brandy?
Yeah,
You don't have to say that. Anyway, so I mean, it's an opportunity to spend some time in the lab during the summer, and it's a paid job. And so, you know, not only are you, you know, do you have a paid job, but you also have experience then in the lab, and it's something to put on your resume. You know, as you go looking for jobs and you look to further your experience. Also very good for graduate school, medical school, that kind of thing. So, and then, you know, how does the lab fit into medical school? You know, how many of you are interested in medical school? Pretty much everybody. Pretty much. You're okay. You're interested too. Yes. Okay, so our assistant previously, well, we had Brian, but prior to Brian, we had Chris Tapia in the lab. Chris helped us for about 2 years, and Chris went on to medical school. So he wasn't from Dominican. He was from Berkeley, but he had no background in science, and he thought, you know, I really need some science courses and some science background. So he took some classes at Marine Community, and he worked in my lab, and he also worked part-time in a doctor's office where he could get paid something. So that together, those things allowed him to get a successful application to medical school, and he's now attending Northwestern in Chicago, Feinberg School of Medicine, an excellent medical school. So how many of you guys went to the seminar last night? A couple of you. So okay, so you heard about Tasha Khan and what she did to get into medical school. So that's, you know, an interesting perspective. The people that I know that have been successful are pretty directed. You know, you need to be thinking pretty specifically about that and making the most of your time and trying to grab opportunities when they come your way. So I think the lab is definitely a big thing. Everybody that I know that has been successful in medical school also has background in the lab. Why is that? Why would the lab be important for medical school? I mean, it seems like medicine, you have your white coat, you're dealing with patients. Why do we need to know lab stuff? It seems kind of distant, maybe way too much detail, more than you need to know, that kind of thing. Why do you think that it ends up that way? Well, first of all, I mean, one way to look at it is that the doctors that are interviewing you for medical school, the doctors that work at medical schools, those are research doctors. They're not really the general practitioners or so much the medically practicing doctors, right? So they're educational, but in the educational environment, the way that you learn more is by researching. So you find out new things. So therefore, the people that are going to select you guys are academic and they're research oriented. So you're going to have an advantage if you present yourself as academic and research oriented student interested in attending the school. So that's something to keep in mind. That's an interesting perspective. As long as I'm going into perspective, I love generalizing. So just let me indulge this for a minute. So there's medicine. But there's a lot of other things out there too, besides medicine, and there's a lot of things related to medicine. Give me some other application of biology in general. You guys are probably bio majors, chem majors, whatever. So applications for biological knowledge, biotechnology, environmental. Okay. So ecological maybe. Or ecological remediation is one of the things that Okay, any other ideas? What can you do with your knowledge of biology besides medicine? How does this break down? What about the food you eat? Okay, food is biology, right? We're biological organisms, so it's interesting to consider our medical needs, but our daily need is bread and food, right? So food production is a big deal. And food production is increasingly engineered. We have a lot of people that we need to feed, and you wonder, well, how can we feed so many people? And the population goes up billions and billions and billions, and still we're doing a pretty good job of feeding people. Why is that? Well, it's because the crop yields and stuff are much higher. And the reason for that is because those crops have been engineered. So there's a lot of good that comes from it. We're all fed. But there's also possible problems from that too. We'll discuss that in a minute. Anyway, so we've got food. Another item, just in general, I would say industrial. Some of industrial can sometimes go into the food thing, but there are a lot of other products. Give me an example of a sort of a biological, an industrial product, something we use every day. Yeah. Toothpaste. Everybody here use toothpaste every day? Did you use toothpaste this morning? Toothpaste. I don't know. What made you think of that? I was trying to shape this piece of paper. I wanted to use paper as an example. Paper is a product from wood, right? So we use a lot of paper. Even in the digital age, we're using a lot of paper. So, the processing of paper is a huge deal, and it's done on an industrial level. And there's this huge vats of paper pulp. And the way it was processed is using genetically engineered enzymes today. It used to be chemical processes, but the chemical processes had a lot of waste. And the waste went into the water supply and that kind of thing. And the pH of those solutions was really off compared to what neutral pH would be. So there were a lot of problems with that. So there was some advantage to using industrially engineered enzymes to produce things like paper. And certainly for food, a lot of things. So do any of these other areas sound interesting to you? A little bit, right? So I want you to be open to that too. I mean, as much as medicine is really interesting. I have a bias towards medicine myself. I was a faculty member at Stanford Medical School in a dermatology department, and I enjoyed having medical colleagues, and it's an interesting perspective. But it's not the only thing, and related to medicine, of course, there are a lot of other lab type jobs. Give me an example. If you're not a doctor per se, but you're doing something medical, what can you imagine yourself doing? Pharmacist, okay, that's decent. Good idea. So along that lines with a pharmacist is the person that's actually metering out these prescription drugs. But what about all the people that are developing the drug? They're sort of they're in a medically related field. It's pharmaceutical industry. So how big a deal is the pharmaceutical industry? It's a pretty big deal, right? I mean, as far as medicine goes, they've got a big part of the influence there. You go to a medical conference, you're going to come head to head with the pharmaceutical industry. They're supplying the doctors with the treatments. So, and there's an important symbiosis there. If they didn't provide decent drugs, the doctors wouldn't be able to help you as often as they can. So, it's an important thing. How about biotechnology? How does that relate to this whole thing? Does that feed into medicine? It kind of feeds in through pharmaceuticals, right? Pharmaceutical industry is the traditional classic method of developing drugs. You find small molecule compounds, organic compounds. You put them in pill form. Sometimes they're injected, but usually oral doses. And then they were originally plant derivatives, right? And then why was that? Well, it's because we're all tribal people, right? But we're in the modern age. We're derived from tribal people. And within the tribe, there was somebody that knew something about, if you use this certain leaf and you smear it on your skin, it reduces the itching, or it might, help heal bee sting, or something, make it less sensitive, or something like that. So, there were compounds out there that were derived from plants originally. So, so all that stuff feeds into medicine, pharmaceuticals, biotechnology. I like to watch science fiction movies. I don't know about you guys, but in the science fiction movies, a lot of times some of this stuff goes wrong, right? So how can this whole thing that we're doing with the bio knowledge, how can that go wrong? Anybody else here watches these sort of movies? I watched was the new Planet of the Apes one recently? The Rise of the Planet of the Apes. And so what they were doing was the research lab was focusing on Alzheimer's, much like our colleagues at the Buck Institute. And they had a lead compound. They were testing it on monkeys to see if their cognitive abilities increased with the treatment of the drug, and it did. And then, of course, you can project forward what would happen if monkeys became very smart. And at the same time, there was a detrimental effect to humans. So the humans got sick, potentially even died from doses of this drug or exposure to something related to the drug. So then you have to Rise of the Planet of the Apes. So there are things that can go wrong, and I think it's worth noting that. So industrial, I don't know, industry can produce pollution, right? So I personally believe that there's something called biological pollution. So that's, if you're genetically engineering enzymes to do an industrial process, and some of these vectors get out with the sequence for altered enzymes that are not, they're not normal to the environment, and they're able to degrade certain substances like wood in the environment, etc. You can have a problem with that, so there could be a biological pollution from that. In the movies, in medicine, rather than curing disease, you might create a disease. During the HIV epidemic, there were certain countries that were sure that this was a genetically engineered virus that came from a U.S. research lab. So I would doubt that. Nonetheless, the potential is there. Certainly in biological warfare labs, they can make viruses that will kill people. So things can go wrong with that. And then, the food production thing, of course, it's kind of related to the biological pollution, but there could be some ecological ramifications of that. Ecological, call it destabilization. So those are problems. And so whenever you come up with solutions, you also create new problems. And then you need people, newly trained people like yourselves to solve some of the problems that were created while we were trying to solve other problems. So it's a continuous problem, and progress needs to be made at every level. Anyway, so I just wanted you to consider that because besides just focusing on this central medicine, there are related fields that you guys can go into, and they are interesting. And I think medicine itself is going through a transformation. As the technology gets better, it's really a question, if you want to be in medicine, it's like, well, what technology do you have to offer? We had a student in the lab a couple of years ago from Germany, and his father was working with some kind of a ultrasound device or whatever, and so that's what he provided. He was the expert at using this diagnostic machinery, and he had a great life. He had a big family, and he was very happy, and but he had a specialty. So he wasn't just a general practitioner. He was trained to use a particular high-tech instrument that requires a lot of expertise. So sometimes, if you want a medical career, the way to do it is get to be good at a certain thing. Okay. Related to all this, I made mention about, jobs. And, these days, people are pretty sensitive to what they're learning and what you can use it for. My daughter goes to college at UC Davis. And actually, Bandit graduated from UC Davis. And sometimes she says, well, Dad, I took this class, but I'm not convinced that there are any jobs in that. I could get a job teaching the same thing, but there isn't really an application for that stuff. And so, one of the things that I think is nice about our lab experience, especially our group, is we have a lot of instrumentation, and there's a lot of things that we could look at. And those skills are the skills that you would need if you went into a commercial lab. If you get an internship somewhere else, like at the Buck Institute, or you go into the master's program, and you could be at the Buck or BioMarin or here. Some of the skills that you've learned are going to be directly applicable. So you're learning, the trade. You're learning these skills that have real application. So the more things you learn technically, the bigger your tool bag is. You know how doctors have their essential, their medical bag? But these days, I think your medical bag is really the technology that you've accumulated, proficiency in using a bunch of techniques and equipment. So that's what you signed up for. I hope you're ready, because that's kind of my approach. Okay, so let's talk about the lab. First thing I want to talk about as far as the lab goes, and this is really unique, Uh, but from my perspective, it's quality control. It's like the last thing you hear about. Actually, people go right through their PhDs and never see this phrase, quality control. But I like to emphasize that because without quality control, the experiment is not reproducible. It's pretty annoying. That means you're going to have to redo the same experiment over and over again. It means that it's very difficult to interpret what the results are. Well, we did it, but one of the reagents here I left out over the weekend. It says to store it at -20. Do you think it's still okay? Probably not. It's probably not okay. So, these issues of correct storage of reagents, what their shelf life is. We have a chemical here. It says expired 2004. Is it still okay? It might be. But they put an expiration date on that chemical for a particular reason, and that is it can't really be trusted past the expiration date. So it really makes sense to try to stay within those parameters. So therefore, the key to doing experiments really has a lot to do with quality control. And from my perspective, I'm much more industry-oriented. So from my perspective, you guys were working for me, I want you to think about this concept of quality control. It's like, unless you can tell me that you did it the right way using good reagents, whatever, that, then I just can't interpret your results very easily. And it's like, well, Professor, I worked really hard on this. I've been working on it all month. And, this is what it looks like. And I don't know why we were not able to get this thing. So, well, what about the reagents? How are they looking? And, I didn't record anything about the reagents. I think it was this tube over here on the shelf that I used. Are you sure? What about this tube right next to it? Looks the same. Oh, yeah, it could have been that one, too. Oh, okay. So, it gave us this result either because that's the way the system works biologically, or because you use this chemical reagent that was already expired or whatever, right? So this is a really big deal, quality control. So what do I want you to do? I want you to be aware of all reagents that we use in the lab. Sometimes we're giving you aliquots of things, so we'll try. I guess we're going to try to put expiration dates and stuff on some of these things, so you can record that. But you should be recording what it is that you use. Where do you record all of this information? In a book. What kind of book? Yeah. Lab notebooks. Big deal. You guys have heard about lab notebooks. People have lectured about lab notebooks and books on lab notebooks. The lab notebook is your document. It's for you. It's not for me. I don't care that much about your lab notebook, but in this class, I'm going to look at your lab notebook. Because that's part of your training. And I want to be convinced that you're taking this seriously. Like, if you don't write down something about the reagents that you used in your lab notebook, that means you don't care enough to do that. So if I see a job opening at BioMarin and they say, oh, Dr. Heffler, do you have anybody to recommend for this job opening? And I'll think, I was like, well, I could recommend this person, but let me see, they never recorded anything in the lab book, I don't know if that's going to work out very well. So just by being conscientious and, going through the steps that you need is going to make a difference down the line. Okay, so under quality control, let's just write a couple of these things. So the temperature that it's stored at, the shelf life, so the shelf life, and then under that expiration date. Also just observations. I added this white powder, but it was clumpy. you know, and it was, a lot of it was very clumpy. Well, just write that down, you know. Powder was clumpy, you know, use the granular part, you know, whatever. Something that you can describe what you saw, what you worked with. Okay, that's kind of general stuff. Did you guys see this? I posted this. This is the syllabus. I just posted it last night. Anyway, so it's available online on Moodle. So this is what you're going to be doing week after week. It's very helpful to have that. So the interesting features of this are, one, we're going to have some quizzes. And the reason for having quizzes is that it's a realistic way to see if you're getting it or you're not getting it, right? I mean, you know, I know that you guys don't really relish the thought of being quizzed on stuff, but on the other hand, like let's say I give you a C plus in the class. You're gonna say, well, Dr. Heffler, I think I deserve more than a C plus. I mean, aren't you gonna like be limiting my chance for medical school? And and I'll say, well, yeah, I didn't want to give you a C plus, but you know, I didn't like the way you worked in the lab. You know, I didn't trust your results or something like that. Well, it's like, well, but Dr. Heffler, I got the results I was supposed to get, right? So, I mean, it could be too much of a subjective judgment. I don't, you know, some people are friendlier and happier or whatever, more outgoing, etc. But that's not really what's going to determine your grade. It's really going to be determined by what you know, and if you're competent at doing what you do. So, I'm willing to entertain all sorts of personalities and, you know, different styles. And the way I can check on what whether you know something is by giving you a quiz. So you remember doing the rotation in my lab, we had a quiz, right? Do you think that quiz was fair? Sort of. Kind of, sort of. It was a little bit detailed. So we're going to have, you know, a couple of quizzes like that. So those are written on the schedule here. Our first one is September 7th. So it says quiz on previous labs, including this one on that particular date. So let's see, and the next one, there's just a few. So October 5th, here's a quiz on previous labs. And then also November 16th. So there's three opportunities there. So what's likely to be on a quiz? What do I care about? This is a lab course. This is not a lecture class, right? I mean, we're going to have a lecture just to help orient us, and it will help you in the end. You won't be so lost in the lab if we understand what it is we're doing. On the quizzes, the number one thing. Well, give me some examples. What do you think I might ask? If we do an experiment, what am I going to ask? Yeah, good. Thank you, Brandy. You know, I mean, what is the purpose of doing this experiment? I mean, we did something, we saw something, and then we conclude something about what we observed. So, you know, within that conclusion should reflect on the purpose for doing the whole experiment at the beginning. Now, the experiments that we're going to be doing this semester, basically we know the results, right? But you guys need to be brought up to speed. This is 3-semester class. So at the beginning, we need to make sure that you show some competency in each one of these techniques. And it's not just techniques, though. We want to illustrate some biological concepts to you, get you thinking about cells, especially like cells. But there's some related topics too, the molecular biology aspects of cells. That's also included. Okay, so you'll be following this. Then the experiments that are done will typically have a lab protocol, and you'll learn how to read a lab protocol and follow a lab protocol, and that's a useful skill. That really is a particular skill set that's not trivial. If it's written in the protocol to incubate for 10 minutes, is it okay to incubate for 20 minutes? Maybe or maybe not, you know. Usually people are in a rush. So it's like, well, I didn't want to wait 10 minutes, so I waited 2 minutes.
Now I look at the results and I can't really see much. It was supposed to turn blue, and it sort of looks very light blue maybe. It's like, well, maybe that's related to the fact you incubated for 2 minutes instead of the 10 minutes. You know, so you know, try to follow the protocols. That's one of the reasons why this is a long class, right? You know, experiments, you remember this from doing some of your experiments, right? There's an incubation step. And it says, you know, put it in the incubator. And it might be 30 minutes. What are you going to do during that 30 minutes? Talk to your buddy. You can do that a little bit. I mean, you know, that's one of the things I expect. I expect you guys to talk to each other a little bit. And in fact, actually, I think when we do the experiments, it's probably a good idea to partner up with somebody. Nonetheless, we're kind of sensitive to the fact that sometimes there's a more aggressive partner and a less aggressive partner. We want to make sure that everybody does the procedure. You know, make sure you have some hands-on time. You know, I mean, your best friend might be, you know, a good friend, but they tend to hog the tissue culture hood or whatever. You know, make sure that you get in there too. And so we'll have some labs specifically where we make sure that there's lots of cells and lots of plates and stuff there for you to work with, so everybody gets some hands-on. Nonetheless, it is kind of cramped, right? So we're going to be in 223, and we've got a lot of instrumentation there. So I think that's a plus. I mean, we have an extra nice thing to offer you, and that is that it's an advanced lab, similar to what you would see at the Buck or BioMarin or UCSF or, you know, Berkeley or wherever. I mean, you know, it's pretty much a state-of-the-art type of lab. So that's the good thing. On the downside, that means that we have kind of one of each type of piece of equipment. So that means, you know, you got to kind of wait a little bit sometimes to use the thing that you need to use. And there's somebody else looking in the microscope. We actually brought in an extra microscope just to alleviate some of the pain there on just basic cell viewing. But that's one of the less than ideal aspects. Nonetheless, so what we're going to do is we're going to try to rotate you guys in. We're going to try to do different activities with a subgroup. And that's one of the great things about having Thanda volunteering to assist us with this lab, because she can take one of the groups and I can take one of the groups, right? So we can split the class in half. And suddenly you don't have to wait for all, you know, 10 people or whatever to do something. You just need to work with a couple of people. So then it will go faster and it'll be clearer what to do. Okay. So that's sort of the general overview. Also at the end, I want to report one of the experiments that we're doing next week, not today, but the next session, is we're going to start on growth curves. So we're interested in how cells grow over time, and you can watch them, you know, basically double, you know, every couple of days. So you're going to get a curve. But the curve is going to tend to, you know, it's going to vary some, and you're going to get a chance to see how does it vary. And in order to get a growth curve, you're going to need to count cells, right? That's one of the things about cells. You can observe them and look at them and say, well, this cell looks like this or that, and that's important information. But just the number of cells is a big deal. One of the numbers I always throw out is like how many cells are in the human body. I think that was on our quiz, right? And so there are numbers that vary. I kind of like the 13 trillion number, but you know, some people quote 50 trillion number, so it's somewhere in there. So if I ask you how many cells are in the body and you say billions, that's not enough. So that's the wrong answer. And if you say, you know, gazillions, that's, I don't know, that's too many. Or a Google type number or something like that, that's too many. Okay, so there are a definitive number, but there's a lot of them. So 13 to 50 trillion cells. So the growth curves, we're going to need to do cell counts. Anybody have an experience with doing a cell count? Randy does, because she was in our lab. Yeah, and Michael a little bit. So you used what? The slide thing? Yeah, it's a hemocytometer. And it's a slide with a grid etched in it. And you squirt the cell sample in there, and it allows you to count how many cells. Why would that give you the cell number? Do you just count the cells that are in the drop of suspension? How would you get the cell number from that? We're going to be doing this right after we leave this room. So this is now we're talking about what we're actually doing today. So so pay attention to this. So the hemocytometer, it looks like a thick glass slide, and there are side rails here, and in the middle, there's kind of a silvery grid. And it looks like a big tic-tac-toe board, but there's lots of extra lines too. Besides the main tic-tac-toe board, there's like lighter lines too, which kind of confuse everything. So that's what the hemocytometer looks like. And then you're going to put a cover slip on here. So there's a piece of glass that fits precisely on these rails. And actually, it's good on these rails if you could slightly wet them, get them a little bit damp. And then you take the slide and you move it back and forth with your thumb, and the cover slip sucks down to that surface. So that's important, because if you put a drop on a slide, that drop could look like that, right? Depending on how much you put in there. It could be a big drop, or it could be kind of a flatter drop, whatever. Well, the size of the drop is going to affect how many cells are in that volume very directly. So the way actually the hemocytometer was designed is this cover slip forces the drop down to be a very specific size. It's, you know, the guardrails are here along the sides. And so this volume in here is 0.1 centimeters. Exactly. Well, okay, so if you know the height of something, then the other dimension on the grid, well, we've measured that already. We figured out, you know, within one of the squares on this tic-tac-toe board, that is 1 square centimeter. It's a centimeter in each direction. So you can actually count several squares. So call this one number 1, this one 2, this one 3, and this one 4. Okay, well, what about this one here, or the center one, or this one over here, or this one, or this one? Well, yeah, they're all the same. They're all a square centimeter. But convention, I mean, people often will count the outside squares because it's the most spread out. So within the drop, you know, there might be some variation of those cell numbers within the drop, and if you go to the 4 corners, feeling is you've got kind of a representation of the whole field. Like, let's say there's more cells on one side of the drop and a little bit fewer on the other. You're going to pick that up when you count all 4. So you count all 4 and you average them. You add them up together, divide by 4, you have the arithmetic average of that field. And then from that, you can calculate how many cells per mil. So do you have an idea how that works still? Yeah? Can you put that together? Or you need me to give you more information? So remember that we were saying that there's a centimeter by a centimeter by a tenth of a centimeter. So what does that equal to? So it's 1 centimeter times 1 centimeter times 1/10 of a centimeter. Morning. See, that's why we try to record the lecture, in case people show up. Traffic?
My alarm clock.
Oh, that's a good one. That's it. So we were just talking about the hemocytometer and how we calculate cells per mil. So we're dealing with centimeters. How do we get from centimeters to mil? And, you know, a centimeter times a centimeter is a square centimeter. So, and then times another centimeter is going to be cubic centimeter, right? So that's a real volume in the 3D world, X, Y, Z coordinates, the box, right? So that's a volume, a cubic centimeter. So how does that relate to a mil?
Isn't it equal to?
It is. Very good. Thank you. Yeah, so, you know, like when you watch the medical shows on TV and, you know, one doctor's talking to the other and it says, "Doctor, give me a syringe with, you know, 5 centimeters, 5 cc's of phenobarbital or, you know, epinephrine or something." Well, you know that those 5 cc's are 5 mLs. You know what that looks like. You've worked in the lab, you've drawn it up in your pipette, you've delivered it into a flask or whatever. You have gained some experience with what 5 mils looks like. So 5 cc's used medically is equal to 5 mils. The only disconnect is kind of in our regular lives where our society hasn't switched over to the metric system, right? So we're still dealing with fluid ounces and things like that. So, but you know, definitely think in metric units. Think grams. Think mils and liters, and also moles. You guys have some background in chemistry, right? So, okay, so this volume is going to be 0.1 cubic centimeter. So that means it's, you know, 10 to the minus 1. And then you count what's in the field, and you take that. We counted these 4 sectors. We averaged them. So let's say that number is 50. So I mean, we averaged, you know, 49 and 51 and 47 and 53. Those were the counts you got from all these, and you add them up together and divide by 4, and you get 50 for the average. Well, this number times 10 to the 4th is going to be the cells per mil. So the number you get, and then this is the magic number, 10 to the 4th, is equal to cells per mil. And so the cells came from a dish, let's say. And so in order to get them out of there, you put in trypsin EDTA solution, and put them in the incubator, and then you remove that supernatant, and let's say that's 3 mils. 3 mils of cell suspension. So if you know those cells per mil, you have to multiply by 3 to get the total number of cells in that vessel. So cells per mil, and then times ml is equal to total cells. Okay, so we're going to do that today. We're going to count cells in the hemosatometer. Because we're trying to prepare you guys for next week. So this is the first lab, so you know, we're sort of anticipating some disorientation a little bit. You know, you're kind of new to the room, we're new to each other a little bit. So, you know, we want to ease into it, but we're going to give you some skills that you need for next week. So we're going to start with the growth curves next week. So you need, you know, this week you need to understand, well, how does this cell counting thing work? So we're going to do the operation where we trypsinize the cells and give you the cell suspension. Right, then? We're going to give them that, right? And then you guys are going to put it onto the hemosatometer, and you're going to give me cell counts. You're going to show me that you counted these 4 sectors, and that you were able to calculate how many cells per mil that is. And nobody's going to ask me, how do I do that? Because I just told you. You get the average here, you multiply that by 10 to the 4th, and that's cells per mil. And you need to know how many mils there were total. And Thando will know that. It's going to be a number like 3 or 4. Right? So then you'll know the total number of cells in that vessel. Okay. So this is sort of the classic cell counting method. And then there's a more modern method